Hello everyone, welcome back to Gyanway. So today we are going to start a new series on GATE 2017 Chemical Engineering Solutions. So today's agenda is chemical reaction engineering. So without wasting much time, let us start with our first numerical which came in GATE 2017 for the subject chemical reaction engineering. So the first numerical is the following reaction rate curve is shown for a reaction A gives P. Here minus Ra and Xa represent the reaction rate and conversion respectively. The feed is pure A and 90% conversion is desired. So 90% conversion is desired. So in this graph 90% conversion will be somewhere around here. So now we have to find which among the following reactor configuration gives the lowest total volume of the reactor. So four options are given: CSTR followed by PFR, two CSTR in series, PFR followed by CSTR, and a single PFR. So let us consider for the first option, second and third option, the conversion after the first reaction be 50% and 50% will be somewhere around here. So now we know that area under the curve gives the volume, gives the total volume required for the reactor. So now first option is CSTR followed by PFR. So we know that for the CSTR it is the area under the curve will be rectangle. Since it is simple multiplication, the design equation there is simple multiplication, so area under the curve will be like this for the CSTR. So now CSTR followed by PFR. For PFR, area under the curve will be somewhat like this. So now this total area will give the total volume required for the reactor. So now second option is 2 CSTR in series. So 2 CSTR in series will be 2 CSTR. The first CSTR will be like this, and for second CSTR the area under the curve will come like this. So now we can clearly see B option required more area than A option. So we can say A is less than B. A required less volume, and the first option required the less volume than B. So now third option is given as PFR followed by CSTR. So PFR followed by CSTR. So now PFR followed by CSTR, let us understand with this. PFR followed by CSTR. So for PFR 50% will be around somewhere here. So now for PFR followed by CSTR, it will be like this. Area under the curve will be like this, followed by CSTR. Then CSTR will be like this. So now we can clearly see again in comparison to the first option, this option required more volume. So now again, comparison to the B and C, A require the less volume. So now let us see the fourth option, which is given as single PFR. So for single PFR, it will be 90% will be here, and for single PFR, the area under the curve will be totally this one. So now if we will compare the volume required for the first option and volume required in fourth option, then we can see this complete part is left. So we can clearly say area for the first option is less than the area required for third option. So answer for this question is A, and CSTR followed by PFR configuration gives the lowest total volume of the reactor. So now let us move to the second question. The second question says consider a first order catalytic reaction in a porous catalyst pellet. Given R is characteristic length of the pellet, D is given as effective diffusivity, Kc mass transfer coefficient, we already know, K1 is rate constant, and Cs is concentration of reactant for the pellet surface. Now expression for the Thiele modulus is, so we know that we should learn the expression for Thiele modulus. It is L root K upon D, where L is given as the characteristic length and K of the pellet, and K is the rate constant, and D should be the effective diffusivity. So here in this question, L length is given as R. So now the correct option will be B for this question. So for this question, the correct option is B. So now coming to the third question for the CSTR, it is again the very simple question in GATE 2017. The GATE 2017 was one of the most simplest paper up to now for chemical engineering. For a solid catalyzed gas phase irreversible reaction, which of the following statement is always true? So for solid catalyzed gas phase for reversible reaction, which of the following statement is always true? So now we have to find the true statement. So adsorption is rate limiting. Second is desorption is rate limiting. We cannot infer. We cannot infer from the solid catalyzed gas phase reversible reaction that what will be the rate limiting, adsorption or desorption. Rate limiting step completely depends on the experimental value. So now third option is given, fourth option is given as temperature does not affect the equilibrium conversion, but it affects. Now third option is given as solid catalyst does not affect equilibrium conversion. This is true because catalyst only increase the rate of reaction, increase or decrease the rate of reaction. It is used to elevate the rate of reaction. It does not actually affect the equilibrium conversion. It is used to affect the rate of reaction. So answer for this question is C. We can clearly see it is the direct question which came in GATE 2017. So the next question is, the reaction A gives B is carried out in a reactor operating at a steady state, and 1 mole per second of pure A at 425 degrees Celsius enter the reactor. The outlet stream leaves the reactor at 325 degrees Celsius. Heat input to the reactor is given as 17 kilowatt. Heat of reaction at the reference temperature is given as 25 degrees Celsius is 30 kilojoule per mole. A specific heat of A and B are given. The molar flow rate we have to find leaving the reactor. So we have to find the molar flow rate of B leaving the reactor. So now when we will apply the general mole balance, so general mole balance will be in minus out plus generation equals to accumulation. So in will be Cp nu I T minus Ti minus Tr. Out will be Cp nu naught T naught minus Tr, and heat input is given, so plus Q, and heat of reaction will be delta H and RAV. So this will be minus RAV. This will be minus RAV. So now when we will apply the unit balance, so in this Cp is given as kilojoule per mole into Kelvin, into nu I is mole per second, into Kelvin. Temperature is Kelvin. So this will come as Kelvin will be cancelled, mole will be cancelled. So this unit will be kilojoule per second. So this unit will be also kilojoule per second, and this term unit will be it is given as kilowatt. So kilojoule, again kilojoule per second, and now delta H is given as delta H is 30 kilojoule per mole. So delta H is 30 kilojoule per mole. RA unit is mole per meter cube second into meter cube of volume. So meter cube cancel, mole cancel. So again unit is kilojoule per second. So now we know that here RAV is not given in the question. There is no rate of reaction, plus there is no volume given. So we know that tau equals to V upon nu equals to Ca naught into X upon minus Ra. So from here we will get C minus Ra into V equals to Ca naught into X into nu. So now minus RAV into Ca naught X into nu. So reaction is given, A gives V. So it is not given it is complete or incomplete. So we will consider it as complete reaction. So Ca naught into nu. So X will be 1. So Ca naught into nu will be Fa naught. So minus RAV came out as FA naught. So now when we will put in this reaction minus RAV, we can replace it as FA naught. So now when, on putting the value, so CP value at the inlet is given as 0.1 into nu I is given as 1 into Ti minus Tr, so 425 minus 25 plus Cp is given at the outlet 0.15 and nu we have to find, and T naught is 325 minus 25 plus heat input is given 17 and heat of reaction is given 30. So heat of reaction, it will be exothermic, so minus 30 into FA naught. So FA naught is 1. It is inlet flow rate FA naught 1 mole per second. So now when we will solve it, it will be, for this term will become as 40 plus 300 into 0.15 into nu plus 17 minus 30 equals to 0. So the answer, when we will solve this, the answer will come as 0.6. So answer for this question is 0.6. So now the next question is, the curve C, the C curve measured during the pulse tracer experiment is shown below. So in the figure, Ct is the concentration of the tracer measured at the reactor exit in mole per liter at time t second. So we have to find the mean residence time rounded up to 1 decimal place. So mean residence time we have to find. So we can simply, this question is direct question, we can simply see that the curve is symmetric about this axis. So it is symmetric at 1. So the mean for this question will be 1. So answer for this question is 1 second. So now this was a direct question in GATE. So now next question is, the following liquid phase reaction or second order reaction is carried out in a isothermal CSTR at a steady state. A gives R. So rate of reaction is given where Ca is the concentration of the reactor, reactor volume is 2 meter cube, inlet flow rate is given 0.5 meter cube per hour, and inlet concentration is given. We have to find the final conversion rounded up to 2 decimal place. So we know that tau for CSTR, for general, when we will apply the general balance for CSTR, then design equation come as tau equals to Ca naught minus Ca equals to minus Ra. So tau is nu V upon nu. So volume upon volumetric flow rate. So minus Ra is given as 0.005 Ca square. So this will be the question. So now when we will put the value of all these things, so we have to find the fractional conversion. So that is Xa. So V by nu equals to, we will solve it, Ca naught minus Ca will be Ca naught 1 minus X upon 0.005 Ca naught square 1 minus X to the power whole square. This came because Ca equals to Ca naught 1 minus X. So now on solving, we will get V upon nu equals to Ca naught into X upon 0.005 Ca naught square 1 minus X whole square. So 1 Ca naught will be cancelled by 1 Ca naught. So now we have to find X from here. So volume is given as 2 and inlet flow rate is given as 0.5 into 0.005, when we will cross multiply this, into Ca naught is given as inlet flow rate is given as 1000 mole per meter cube. So 1000 mole per meter cube. So now equals to x upon 1 minus x whole square. So when we will solve it, then it will be x upon 1 minus x whole square equals to 20. So now solving x equals to 20, 1 minus x whole square. So x will be equals to 20 x square minus 2x plus 1, or 20x square minus 41x plus 20 equals to 0. So when we will solve this equation, we will get the final answer of x as 0.5. So now this is the final answer, this is the final conversion, fractional conversion 0.5. So now the last question is, the following gas phase reaction is carried out in a constant volume isothermal batch reactor. So we have been given isothermal batch reactor, and the reaction is given A plus B gives R plus S. So the reactant A and B as well as the product S are given as non-condensable gases at the operating temperature. So now the saturation pressure of product R is given 40 kilopascal. Now it is given initially the batch reactor contains equimolar amount of A and B. So 0.5 is A and B is also 0.5. Now at the total pressure of 100 kilopascal, so total pressure is 100 kilopascal. The initial concentration are given for Ca0 and Cb0. The rate of reaction is also given. Now we have to find we need to find the time at which the R just start condensing. So now when R will condense, the R will condense when the pressure will become lesser than saturation pressure. So saturation pressure, when the total pressure will become less than saturation pressure, then our product R will start to condense. So our reaction is given A plus B gives R plus S, and initial pressure, this is the initial condition, we can say initial condition, A plus B gives R plus S. Now at initial condition the total pressure is given 100 kilopascal. So 100 kilopascal, we can say that there are two components, so this will be 50 and this will also be 50. So 50 is A and 50 kilopascal we have given for B. Now we need to find the time at which R just start condensing. So R will start to condense when the pressure will become less than 40. So at 40 kilopascal, the reaction will be A plus B gives R plus S. Now at 40 kilopascal, all the four components will be present, A, B as well as R and S. So the pressure will be given for each of the component will be 10, 10, 10 and 10. Now we can say final minus initial, 50 minus 10 for A upon 50 equals to XA. This is nothing but CA is equals to CA0 1 minus XA. So 50 minus 10 upon 50 equals to XA. From here we will get XA equals to 40 upon 50, which is equal to 0.8. So now XA came out to be 0.8. Now we have been given with isothermal batch reactor. Now isothermal batch reactor is given. So for isothermal batch reactor, we know that tau is equal to 0 to XA dCA upon minus RA, or tau equals to this is CA to CA, CA0 to CA, CA0 to CA. Now tau will be equals to 0 to XA CA0 dXA upon minus RA. So this is for batch reactor we already have. So when we will put this the value tau equals to CA0 will be, CA0 is already given 12.5. Now dXA 0 to 0.8 and RA is given 0.08 CA CB. Now Initially the feed is equimolar, so 0.5 A and 0.5 B. Now all the things are given for A and B are given equal, so tau is equals to 12.5. we can write 0 to 0.8 dxa upon 0.08 CA 1 minus XA and CB into CB 1 minus XB. Now the conversion will be same because because it is given the stoichiometric coefficient is 1 at the reactant also and product also, and the equimolar feed is given, so CA will be equals to CB. So we can write the final tau is equals to dxa upon 0.08 CA square 1 minus XA whole square. Now here it is already 12.5 and this is nothing but CA naught. So CA naught, 1 CA naught will cancel with 1 CA naught. We will have tau equals to 1 upon 0.08 CA naught integration 0 to XA 1 upon 1 minus XA whole square dxa. Now we got tau equals to 1 upon 0.08 into CA integration 0 to XA dxa upon 1 minus XA whole square. This is 1 minus XA. Now tau is equals to CA is 12.5, so we can write the value 0.08 into 12.5 into dxa upon 1 minus XA. When we will integrate, we will get 1 upon 1 minus XA minus 1. When we will integrate and put the limit, now we will get 1 upon 0.08 into 12.5 into XA upon 1 minus XA. So tau is equals to 1 upon 0.08 into 12.5 will be equals to 1. Now XA we have already been given, we already found 0.8. Now 1 minus 0.8, by solving this we will get 0.8 upon 0.2 and we will get tau equals to 4. So here tau we got equals to 4. So we got the time at which the R will just start to condense, and it is equals to tau equals to 4. So this is the final answer for this question, and that's all for the chemical reaction engineering part GATE 2017. We have completed all the question for chemical reaction engineering. So for more such videos, you can like, share and subscribe our channel, and you can also ask your doubts and comments. You can also ask your doubts in comments. Thank you very much.